Alright folks, we talked about the forces. Now I want to talk about Newton's laws. Newton's first law is also called Newton's the law of inertia, and I already mentioned that if there's no force applied to an object, if the object is stationary, it will keep being stationary. If an object is moving, it will keep moving in the same direction with the same velocity. A better way of saying it is here: every object continues in a state of rest or of uniform speed in a straight line unless acted on by a non-zero force. This figure here is showing it during accidents. We are pushed forward. We get hurt because we've been moving before the accidents, and when the car stops suddenly, we want to keep going due to inertia, and we fly out of the window. We hit the window or so on. That's Newton's first law, the law of inertia. So if there is a force applied to an object, there will be an acceleration, and the acceleration is directly proportional to the force, which is Newton's second law simply. So like this nice question here is telling a car is pulled to the right with a constant steady force. How will its acceleration graph look? If the force is constant, acceleration also will be constant. So this will be the answer. So Newton's second law can be summarized better as a force causes an object to accelerate. The acceleration A is directly proportional to the force and inversely proportional to the mass. And we can express Newton's second law with this simple equation here, which we will be using vastly in this course. A is equal to F over m. And if we want to show them as vectors, A is equal to F over m, we put those arrows, and this tells us that A, acceleration, is always in the same direction as force. We learned that the acceleration's unit is meters per second squared. So we can put that in here, maybe. Mass unit is kilogram. These are all SI units, and when we use SI units for acceleration and mass, the force unit will be Newton. There in the name of this great physicist Newton, who studied this, which is why they are Newton's laws. Now if we have more than one force, what we do is we add them as vectors. As vectors is an important thing here, I have to emphasize, because we have to mind the directions, and we have to do whatever it gets to find the correct F net. Some forces could be plus, some forces could be minus, some forces could have arbitrary directions. We have to find components and find F net, what we will call the total force. And we'll use that F net to find the acceleration. So A will be F net over mass m when we have more than one forces. This is another way of showing Newton's laws, and this is the way I actually like it, but feel free to use either way. Here's an simple question. When a rubber band is stretched to pull a 1 kilogram block with a constant force, so I'm gonna make my ugly picture here. I'm gonna choose blue. Actually, I like blue better. So I have a block, and I am pulling it with a force F. This force is constant, not changing it. And this mass m1 is 1 kilogram. So when we pull 1 kilogram block with a constant force, the acceleration of the block is measured to be 3 meters per second squared. The block accelerates, and again I will tell you, acceleration will be in the same direction of force. 3.0 meters per second squared. I'm gonna ask you also, as you pick the directions, always pick the direction of acceleration and force to be positive in this section of forces and Newton's laws. I know we were doing different for the motion section, but this choice will save you a lot of algebra mistakes. Always pick the direction of A, acceleration, to be positive direction. So this is the first case. Second case, when a block with an unknown mass is pulled with the same rubber band using the same force, so the force will keep constant but different mass. Its acceleration is 5 meters per second squared. So I have another mass now, a different mass. I don't know this mass. I'm going to call this M2. But I'm pulling it with the same force. And it gains an acceleration of 5 meters per second. So A2 is equal to 5 meters per second squared. Sorry. Now, what is the mass of the unknown block? That's what the question is asking me. What is M2? And forces, acceleration, masses always will remind me of Newton's second law. Either I'll use it in this format, A is equal to F over M. I'm going to generalize here. We have only one force, but I'll still put F net to keep you guys on board with this. If there is more than one force, we have to find the total. But it's F over M. So inverse proportionality tells me A1 will be equal to F over M1, and A2 will be equal to F over M2. Since they are inversely proportional, right, I can just write this A1 as proportional to 1 over M1. That's inverse proportionality. And A2 will be the same, 1 over M2, not equal, inversely proportional. I can be clever here and just say, to relate these, I can just simply say A1 over A2 should be equal to M2 over M1 if they are inversely proportional. That's skipping some math, and it makes sense. Inverse proportionality will give me that. Simply what we can say is, since the forces are equal, if I divide this whole equation by that, I'm gonna get here. But my logic tells me I can just simply jump and say, well, if they are inversely proportional, that should be the case. And I'm gonna put the known values. We know A1 3.0 meters per second squared, and A2 is 5.0 meters per second squared. I don't know M2, but I know M1 is 1 kilogram. So these will cancel here. This is just 1 kilogram, doesn't make a big difference. Actually, I'm gonna delete this and write it nicer. 1 kilogram. From here I'll find that M2 is equal to 3 over 5 kilogram. That should be 0.6 kilogram. Does it make sense? Our book always tells us this sequence to solve a problem. Draw an ugly picture, what we say, reason with the question, plan what you're gonna do, and then apply what you do, apply the math, use the equations, so carry through your plan, and at the end, once you get a result, think about it if it is reasonable. And this is reasonable because I'm expecting the second mass to be smaller. Since I applied the same force and it accelerated more, it should be a lighter mass, and I found a lighter mass answer. So my answer probably is correct. Here's another one. A constant force causes an object to accelerate at 4 meters per second squared. What is the acceleration of an object with twice the mass that experiences the same force? The same idea. Acceleration is equal to F over M. Larger mass will be smaller acceleration inversely proportional. Here, twice the mass, it's easier to see, should be half the acceleration. So 4 meters per second squared will be 2 meters per second squared. These are fast and easy questions. Another one. An object when pushed with a net force F has an acceleration 2 meters per second. Now twice the force is applied to an object that has 4 times the mass. Its acceleration will be, this is a little bit more challenging, both force and the mass change. So I'm going to write the equation here. A1 will be F over m, and now A2 will be, what is happening, let's read it, twice the force 2F over 4 times the mass 4m. I want to write these now to see. Now if A1 is 2 meters per second squared, A2 will be, if I divide top and bottom by 2, this will go, I'll have 2 here, so it will be 1 over 2 F over m. Now I see on the left my F over m is 2 meters per second squared. I'm going to enter this in here. So this will be then 2 divided by 2, right? When I enter this in here, I'll have 2 meters per second squared divided by 2. Then A2 should be 1 meters per second squared. So my answer should be B. Some of you are really good at reasoning. I can say here like twice the force. That means if I increase force twice, acceleration will be doubled. It will be 4 meters per second squared if I did not change the mass. But then I have 4 times the mass. That should decrease the acceleration back 4 times. So if first increase the force, the acceleration becomes twice larger. It will be 4 meters per second squared. Then if I increase the mass as well, that will divide it by 4, it will be then 1 meters per second squared. So I can also get the same answer logically. But if you guys are confused and you can't go by logic, just do the simple calculation here. So the answer is B. Here's a simple example. We have a basketball. There's a drag force in the air. This could be wind, a breeze pushes it. It's falling down, but there's the wind pushing it. What will be the direction of the motion? Always, folks, the direction of the motion is in the same direction as the total force. So we will add these forces. We can complete this to a parallelogram as shown in here, and the diagonal will be the total force or net force, and that will be our answer. So we will always find the net force if we have more than one forces, and we say the object will go in that direction. It will accelerate if there's a net force, and the acceleration will be in the same direction. And I'm going to find that acceleration using F net over m. We're not there yet, but if I have more than one mass, something attached to the ball, I would be finding all total mass that moves with that force and put it in here as well. But we're only looking at simpler cases now. Here's another simple example. A 40 car train travels along the straight track at 40 miles per hour. Now I have a large train here. It has 40 cars, but I will just draw several. Well, actually, I'll just draw 3. It is going with a velocity x that is constant. Now, if velocity is constant, we learned that the acceleration is 0, right? There's no acceleration if there's no change in velocity. So I got this information now. I'm thinking through the question. Now I learned through Newton's second law that A, acceleration is equal to F net over mass, m. So if acceleration is 0, mass can't be 0. If there's a mass, can't be 0, so F net should be 0. Whenever we have constant velocity or stationary object, no acceleration, no force. Alright, so I got walk through, I draw an angular picture, I got some information that I can deduce from what is given here. 40 miles per hour, constant velocity, no acceleration, no net force. A skier speeds up as she skis downhill. So we have a skier. Good luck with drawing that, but I'm gonna try to draw that. She's skiing downhill. Let me draw that a little bit better with a straight line. So she's accelerating downhill. There is an acceleration here. It's not 0. That means there is a F net on her, and it's not 0. It's larger than 0. That's all the information I can get. On which is the net force greater, we already answered by walking through and thinking about. On the skier, the net force is greater because it's not 0. But it is 0 on the train. So the answer is the skier. Keep in mind, rule of thumb, 0 acceleration, 0 net force. This one we could talk about, but we'll talk about it a bit in more detail. Now, identifying forces and drawing their direction. If we can, drawing which one force is larger, just simplifying our understanding by showing the larger force with a larger vector will be better. But drawing the direction of forces and where they apply to the object is very important in solving questions in this section. So we identified types of forces we'll be using. We'll call force F, weight W. We might have a spring force, F spring. Tension we generally call T, normal force N, static friction, kinetic friction, sometimes drag, and F thrust. So we'll be having those forces. And whenever we have an object of interest, we'll just put them kind of into a bubble and look at what forces are applied to this. Excuse me. Let's find what forces are applied to this skier. He's pulled up by a rope, so there will be a tension force there, and tension force will be along the rope. I'm going to draw this. And of course he has a weight, right, downward. Oh, let's delete that. That was not a good idea. Downward weight. So let's draw that. Now we are not showing components yet, but we know this weight have a component along the surface and perpendicular to the surface, and because he's pushing on the surface will be pushing back, so there will be a normal force. Let me show that. Blue, we have too much red here. I couldn't manage that. Try again. So the normal force, as always, will be perpendicular to the surface. And that's our normal. And additionally, if the question did not mention that friction is ignorable, we will have a friction force. That will always be against the motion. So let's show that as green. And here is our frictional force against the motion downward. And here we go. We'll call this F kinetic, sorry, because he is moving. That's all the forces. Tension, normal, F kinetic, and the weights. And this we will call free body diagram. Again, the suggestion is to take him here, show the object as a point, and show all the forces applied to him on that point. Mainly what we're doing is we're carrying all the forces to one point. We'll put our origin to that point. F kinetic, normal force. These were already put them on his feet on the surface. So pretty much shown, but we additionally have a tension force we want to show here. And this will be our free body diagram with a dot. Again, I like going with the pictures. It helps me seeing the physics better. But this is the technical way of doing a free body diagram. Here's another free body diagram. An example: an elevator suspended by a cable speeds up as it moves upward from the ground floor. Draw a free body diagram of the elevator. Now, in this one, the forces are showed in terms of their representative strength. The elevator is going upward and speeding up. Speeds up means so velocity is upward and increasing. So we'll use a prior knowledge here. If velocity is increasing, acceleration is also upward and increasing. So here is our acceleration. If the acceleration is upward, right away with our new knowledge now we'll say F net and acceleration are always in the same direction. So F net is also upward. And not net, it's net. Let me delete that. Net is a name. F net is upward. Now again, another reminder for this section: if F net is upward, A is upward, because they're always in the same direction, our positive direction will be up. Keep this in mind. And then we show there's only weight pulling this elevator down. Weight is always mg, keep that in mind. Feel free to just replace it by mg. And tension force is pulling upward. That's all the forces. If we're going to compare the strength, which direction we have F net, that force will always be larger. And here is we put it on a coordinate system and draw the forces. That's another free body diagram. Now we got a clue here. If F net is up, the forces that are up will be added to a larger value. We have only tension up, and forces that are down will be added to a smaller value. We have only weight down. That means tension is larger than the weight here. Another example: an object on a rope is lowered at a constant speed. Now it's going down. It has a velocity, but velocity down and constant. If velocity is constant, acceleration is 0. Here's what does this mean. I draw this really bad, but I hope you guys don't mind. Here's what does this mean. There is no F net. F net is 0. If A is 0, F net is 0. It's not in any direction. But there is still this weight pulling me down here, right? mg. There is still this tension pulling me up here. How come I have a 0 net force? How can this be possible? Only way that this can be possible is when I add these two forces. One is up, one is down. They cancel each other, right? So F net here will be tension minus mg, and it will be 0, which means these two guys are equal to each other. Equal and opposite directions cancels each other. Makes sense. So this guy cancels that guy, elevator is going down, or object is going down with a constant velocity, zero acceleration, zero net force. Makes sense? So constant velocity, zero acceleration, zero net force. Another rule of thumbs. This one I meant to ask you on LC, but I have the answer here, so let's look at this as one. An object on a rope is lowered at a steadily decreasing speed. Speed is decreasing, which is true. Speed is decreasing means acceleration is upward. F net is upward, so the upward force is larger. The rope tension is greater than the object's weight. There are some more quick checks here with the answers. Keep in with the same idea, and please review these yourself. I already posted the PDF file for this. I'm going to look at this one. A car is parked on a hill, which is the correct free body diagram, similar to what we did with the skier pulled up. Only in this case there is no pulling up. Right, car is here, there is mg, there is n, normal to the surface always, and there will be a friction force. Friction will be against the motion. I'll redo that. I'll redo the normal as well. Alright, go back. So mg down here, normal force perpendicular to the surface, and friction is against the motion. Actually, friction here will be applying to each wheel separately, but I'm gonna show overall one friction. Now, car is parked means we have static friction, normal force, and mg. So the free body diagram will be looking like this one. Here we go. Here's another one for you folks. A stationary car. No, the car is towed to the right at constant speeds. Draw the free body diagram. We have the answers. Go through these. And I'll do this one and let you go after this. I'm gonna finish this video after this. Consider pushing a block across the table at a steady speed. So we have a table, let's draw that. We have a block. Let's draw that as well. It's a little bit tilted, but it's alright. And we apply a force to that block. So let's apply that force. What else do we know? Steady speed, so it's going in this direction then, and the velocity is constant. Alright. What does that mean? If velocity is not changing, acceleration is 0, F net is 0, right? Right away I put this down. And since you're exerting a force on it, why isn't it accelerated? Identify all the forces and draw a free body diagram. Compare the size of the pushing force and the size of the friction force. So if F net is 0 means there must be a force against my force to decrease it to 0, and that must be the friction. This would be kinetic friction since my object is moving, so I'm gonna call it F kinetic. Additionally, I know there is always the weight of the object. I'm going to show it from the center downward. This is the weight. and I'm gonna call that mg. I just like replacing weight by mg. That's what it is. And there will be a normal force, upward normal force. So here's my free body diagram. Actually, on the picture, these are all forces. We can put arrows on them, or we are showing directions. We can skip arrows. Even the mg is a vector because we have g as vector. But we can also draw this free body diagram here separately. We have mg down. We have friction left, which is kinetic friction. We apply a force in the right direction. We call that F, and there is the normal force. Notice here, since V is constant, A is 0, F net is 0, that means my force is cancelled by frictional force. So the friction force is equal to my force. There is no up and down motion either, so that means my normal force is equal to mg. That's always the case. If I have an object on the system, normal force will be mg, but it should be a flat system. If it's a tilted, that's the component of mg then. Third law, I'll let you go with the third law, is called also action reaction law. When there is an action on an object, if B is pushing on A, there will be a reaction in opposite direction and equal in magnitude. So there is always, they come always in pairs, actions and reactions. Any action brings a reaction, and they're always equal in magnitude, opposite in direction. That's Newton's third law. And better way of saying this, Newton's third law, every force occurs as one member of an action-reaction pair of forces. Examples, we are walking. As we walk, we push on the surface. Surface pushes back with the friction. That's how we can walk. And we know that very well because we cannot walk on a slippery ice, which still has some friction. Zero friction, walking would be impossible. Same with the drive in a car. We push on the road back, and road pushes our car forward. Action-reaction pairs. Thrust force and the gases. So the rocket pushes on the gases, and gases pushes back on the rocket. Action-reaction pairs, and that's how rocket goes. That's how the thrust force works. Keep in mind, they are always equal. Action-reaction pairs are always equal to each other, no matter what the sizes of the objects are. 10-year-old Sarah stands on a skateboard. Her older brother Jack starts pushing her backward. She starts speeding up. The force on Jack, on Sarah, are the same, equal. A mosquito runs head into a truck. Splat! It dies. Truck goes. Still, mosquito exerts the same force on the truck as the truck exerts a force on the mosquito. Same force. Mosquito gets hurt because it's small and it has a larger acceleration, right? Force F net is equal ma, General Newton's second law, or A is equal to F net over m. Mosquito and truck has the same force, but truck has tremendously larger mass than the mosquito, so it doesn't get much acceleration from it, but mosquito gets large acceleration. In another video, I'm going to show some more examples of Newton's laws, and this will be it for this. See you on the